Hello, welcome to lecture number 27. In the previous lecture, we derived that the total derivative of a certain quantity, which is the sum of the planetary rotation and the vertical component of the relative vorticity, is conserved. This product f plus um, the planetary vorticity plus the relative vorticity times the ds. The s is the elementary area of the fluid parcel that we are considering. So this is the circulation for an inviscid rotating system. So this is circulation for this rotating system, but this is all of in these cases we have assumed that the viscosity is zero, so there is no dissipation in the system. So this is analogous. Formulation this formulation is analogous to the conservation of angular momentum of a system where there is no external um, torque been applied. So it is analogous to that formulation. And so if f plus zeta um, must decrease, or if f plus zeta decreases, the fluid parcel, that is the elementary parcel that um, we had taken in the previous lecture. So if the fluid parcel is squeezed, okay, so that means if we have a parcel which is an area ds, and then, or this is an equivalent statement, that is if the parcel is squeezed, the f plus zeta term must decrease. Okay, so this has an f plus zeta and this has an f plus zeta. So this is decreasing, ds is increasing from left to right. We are squeezing the particle and f plus zeta decreases. Now as f plus zeta times ds is conserved, and hds is also conserved because that is the volume, hence their ratio must also be conserved. Okay, that means the total derivative of f plus zeta by h is equal to 0. And this is important for us to look at the expression, because this is the potential vorticity for this system under consideration. This is nothing but the potential vorticity. Okay, how can we be sure that this is a potential vorticity? So we can go back to the original form of Ertel's potential vorticity and see if we can derive this kind of form. And if that is so, hence this is one of the forms of the Ertel's potential vorticity. So remember that we have discussed previously also that Ertel's potential vorticity is a generalized concept. This can have different forms depending on the system that you are looking at. So Ertel's general potential vorticity, PV, has the form the total the absolute vorticity times the gradient of some scalar by the density. So remember that omega here is used in the sense of vorticity. This is not frequency. Okay, in terms of when we are looking at vorticity, we are using omega as the variable. So we can define. I mean, certainly we said that, and during discussion of Ertel's PV, we said that theta can be any function. So in this case, one of the candidate that we can define is, so this is a scalar property. So let's say we define this quantity. Okay, so we have defined that B is the topographic height and Z is the coordinate along which the topography is being measured. So since the absolute vorticity is only in the vertical direction, we find that omega A dot gradient of theta by density can be represented as F plus zeta k cap by rho dot del del z of z minus b by h. Okay, and this gives rise to the form that we have called potential vorticity. There is a rho, but given that rho is a constant for our system, hence F plus zeta by h is a potential vorticity. We can take the density to be 1 for this without any loss of general, I mean, as a without any loss of any information, we can take rho to be 1, given that it's a constant for our system. Now, given that we have PV, we have found out the form of PV on a for a system which is rotating. Now that given that we need PV on a beta plane and a sloping bottom, so we're trying to form the PV on a sloping bottom and the beta plane, we write the PV as F naught plus beta naught y. This is the beta plane approximation, that is F is varying linearly with the meridional coordinate, which is dy, and then del v del x minus del u del y is the relative vorticity based on the velocities which are measured in the rotating frame of reference. Okay, now eta and alpha naught y is less than h naught and beta naught y and zeta is less than f naught. Okay, so then Taylor series expansion of this PV So Taylor series expansion of this expression for PV leads to so this is the expansion for, I mean, the Taylor series expansion of the potential vorticity in a beta plane and the sloping bottom. So we see the from just the expression itself, we can see that, I mean, we'll see the effect of the similar effect of the beta plane and the topography here. There are some observations to make. So as PV increases towards north, so PV increases towards north, that is the meridional direction, that is y coordinate, due to the beta plane. PV also increases towards the shallower side, towards the shallower side of the topography. So we are trying to build an analogy of the beta plane approximation to to a topographical, to a weak topographical feature. So as you can see from here, the potential vorticity increases towards north because of this term. Okay, so it increases towards the north due to the beta plane. PV also increases towards the shallower side of the topography because of the alpha. So okay, so here there's a negative sign in front of it, alpha naught term, and hence it increases towards the negative y direction. Okay, I mean, we have already defined the coordinate system of the topographical feature in the previous classes. So this is one similarity that we can find in for the effect of a beta plane to a topographical feature. This gradient, which is happening because of beta naught and alpha naught in case of topographical feature, is what is giving us the Rossby waves and the topographical waves. Okay, so this gradient in PV either due to beta plane or due to sloping topography gives rise to planetary waves, also called Rossby waves, and topographical waves. And this is what we initially started out with. We discussed that we will see similarities between the topographical waves and Rossby waves, and we'll see, I mean, how gradient in PV creates these, dictates the direction of the waves. But we saw that just because the potential vorticity is being changing, we have, and given the fact that we need to conserve potential vorticity, these kind of gradient which exists due to a beta plane, that is Coriolis varying over latitudes, or a sloping topography, will give rise to waves which will take away the energy. Okay, so let's say we have so this is the planet Earth, and we have some fluid bands at rest. Okay, these are some fluid bands. So fluid bands at rest. Then what we do is, let's say there is something which is perturbing the system. Maybe there's a disturbance, atmospheric disturbance, or an oceanic disturbance, which is perturbing the system. And we'll draw planet Earth again and show the formation of these waves. Let's say we are perturbing the system, and we define our northern um, direction to be the one which is pointing upwards. So the waves, let's say simplistically, I have a wave which is like this, and these are different locations in the wave. One waves in the regions bound by the portion of the wave going upwards, up from the stationary level, and the one which is denoted by 2 is the one which is bounded by the wave which is going, I mean the waveform which is down below the state of rest. So in this figure, you can take a moment and then see which are the regions that are moving into a higher potential vorticity. So remember that this is a perturbation of a fluid at rest, and because of this perturbation we are moving particles away from its equilibrium position. Now because we are moving particles away from its equilibrium position and given the fact that the Coriolis, now the planetary rotation at the different location is different from its initial location. So again explaining things better, let's say there is a location, I mean you have two imaginary locations A and A prime. The planetary rotation at A is different from planetary rotation at A prime. We are assuming that the Coriolis parameter is varying with latitude. I mean, for this to happen, the displacements are to be significantly large enough for the Coriolis parameter to be varying. And if the Coriolis parameter is varying because there is a, because of this factor beta naught y, we know that the potential vorticity will change. In this case, the potential vorticity increases because something has moved upwards, and going upwards PV increases. That means regions 1 and 3 are moving into regions of higher PV. So northward is region of higher PV, and given the fact that region 1 and 3 are now above the state of rest, they move into regions of higher potential vorticity. Okay, so we'll write it down explicitly for understanding. Because F is now more as compared to the state of rest. So now what happens? This implies this implies that they must have negative relative vorticity so that f plus zeta is constant. I hope we are clear on this. So f plus zeta has to be constant. This is what is given by the conservation of potential vorticity, and this is the form that we have derived. F plus zeta should be constant. Now, given that it has moved into a higher PV region, a higher F region, this the relative vorticity should be negative, so that the sum of F plus zeta is constant. Okay, this means, so what does a negative relative vorticity mean? It is there is a clockwise rotation. So these regions gain a clockwise rotation, which is by convention has a negative relative vorticity. So clockwise rotation or a clockwise spin. Similarly, region 2 now moves into a region of lower f. That means f plus zeta to be constant, they should have a positive zeta. And region 2 now moves into lower f. So it must gain a positive relative vorticity. Okay, that means a anti-clockwise rotation. Okay, hence if we try to draw the system slightly better, let's say this is the wave. Region 1 and 2 will obtain a negative vorticity, a negative spin, because f is increasing upwards and it has to conserve its potential vorticity, which was the initial vorticity at this initial potential vorticity at this location. Hence the sum should be constant, and this attains a positive spin, positive relative vorticity. Okay, let's say we have two okay, now we know about the regions 1, 2 and 3. We are clear about these regions, what is happening at these regions. Now I have marked two points A and B, which are at the state of the initial location. The dotted line is the undisturbed state. So these 2 points A and B are squeezed between 2 counter-rotating cells. Okay, hence the fluid parcels at A and B are squeezed between two counter-rotating cells. And what happens if it's squeezed between 2 counter-rotating cells? For example, take something which is being squeezed between 2 moving gears, so it attains a meridional velocity. Okay, if this is rotating this way, it's getting a meridional velocity this way. If the gears are rotating in this direction, they gain a meridional velocity in the upward direction. So this meridional, because this is how we define a coordinate system. There's nothing special about the term, only that now in this planet Earth we are defining meridional to be the y coordinate. So if the gears are rotating this way, the location around, I mean, at the point is moving this way, at the point where they contact. Um, so the fluid parcel in those contact locations, or in these locations where both of these counter rotating cells meet. So in B, so between two counter rotating cells, so they obtain a meridional velocity. So they obtain meridional velocity. So from this figure, we know that A will go down because there is something which is pulling downwards, and there is from the left, and there's something which is pushing downwards. Sorry, there's something pushing downwards from the left and pulling downwards from the right. So A goes down. I mean, the analogy with the gear is just to give you a physical picture. So it's so this point B goes up. Okay. A goes down, B goes up. Now, what happens if A goes down and B goes up? This tries to generate a trough near A. Okay, A is going downwards. That's what we have an intuitive picture. So A is going down, so we are creating a trough. We are trying to create a trough near A, while B is going upwards. That is, we are trying to create a crest. Okay. So, for example, I mean, just to give you some intuitive understanding, something like this might happen. This is so something like this will happen. Not might, this will happen in this scenario. Okay, A is going down, so at a certain later time, if this is t equal to 0, this is t equal to t, this is equal to t equal to delta, let's say delta t. So A is coming downwards, we're creating a new trough, and B is going upwards, we're trying to create a new crest near B, and the dotted line is giving us the change after some delta t. Hence, we see that if this is how the initial perturbation was, this creates disturbance which propagates westward. Okay, so we have already shown that. We already showed that during the dispersion relation derivation of the Rossby waves, we know that the Rossby waves propagate westward. Now we gave you a mechanical understanding, I mean, just with simple potential vorticity conservation and an intuitive understanding of the conservation of potential vorticity and the wave kinematics, we show that this has to travel westward. Okay, so the same mechanism is at play for topographic waves. Okay. So disturbance propagate westwards if the potential vorticity is increasing towards the meridional direction. The same mechanism is at play for topographic waves. Same mechanism is at play and we have already shown the analogy between the alpha naught and beta naught parameters. So this here in this case, the squeezing, so once we squeeze the particles, the fluid particles, into shallower regions, so it causes the F plus zeta to decrease, given that there is a denominator h in the potential vorticity. So we have a denominator h. So this is a shallower region. I mean, and this is the topographic region, this is the reference level, and if we squeeze something, squeeze a fluid parcel to the shallower side, so squeezing causes F plus zeta to decrease given that H decreases. Okay, similarly, if there is a fluid parcel which is going into the other direction, so going into deeper waters, F plus F plus zeta by H has to be constant, so that H now increases. That means zeta, for this fraction to be constant, this zeta becomes, zeta gains, I mean there's a positive zeta. Okay, let's go over this again. So squeezing the particle will decrease H, and given the fact that, so this is situation 2 and this is situation 1. This is situation 1. So squeezing it reduces the H. That means F plus zeta, which is the numerator, should also decrease, because F plus zeta by H has to be constant. If H decreases, the numerator should also decrease. If H increases, the numerator should also increase. That is, the only way for the numerator to increase, if we have an F plane, is for the parcel to gather positive zeta. That is, the relative vorticity should increase. So squeezing causes this, given this H decreases, so this, we can say that parcel achieves negative zeta. Okay, in the second case, if we are going out of the shallower water into the deeper ocean, it gathers a positive zeta. Okay, so these are the two differences, and these are this is analogous, because if you have a wave which is perturbing, and you are perturbing the wave, a portion of the wave into shallower regions, portion of the wave into the deeper ocean, we will have exactly the same condition, that is, the potential vorticity will have to be conserved, and because there will be readjustment needed, there will be circulation which is being generated, as we saw here. This is exactly what is happening in situation 1 and situation 2, that these are gathering these two opposite relative vorticity, and this is causing the waves to propagate. This is exactly the same mechanism that is happening with the Rossby waves. Okay, Rossby waves was because F was varying with latitude. Here this is causing the, now it's causing a change in the height, so that the whole term is being, at least some part of the term is being changed. For the Rossby waves, the numerator was changed. For the topographic waves, the denominator is being changed. Now this is a reason why we can see topographical waves which are analogous to Rossby waves in experiments, because it's easier to change the depth than to change the Coriolis parameter in an experimental setting, which is a pretty difficult task to do. So because of these analogies, we can create topographic waves, and this gives us an opportunity to study the phenomena of Rossby waves, because the mechanism of generation is similar in both the cases. Thank you.